Hello, everyone. Welcome to our live stream. I'm sorry we're getting going a little late today. That is my fault. We were reconfiguring some things to make the stream more seamless. So we appreciate your patience. It's great to see you all here today. We're excited to be with you. We have some questions already from email. And for those of you who are joining us live on stream, here's the way it works. You post your questions in the chat. We have one of our colleagues, Grant, is grabbing your questions from the chat, and then I will try to take those in order, but we jump around to try and make sure we get a variety of people asking questions and a variety of topics. So Chris, I'll hand you the floor so you can welcome everyone, and then we'll get started with questions.
Okay, great. It's good to see everyone. Welcome to live Q&A session for our online courses and for anyone else who finds out where we are and wants to join in. Happy to answer questions about astronomy starting now.
Excellent. The first question is from an email. Wendy asks, is it a majority view that gravity is weak because it leaks into other universes or dimensions? And what is your view?
So the question refers to the idea that physics at a very fundamental level would like an explanation for why gravity is by far the weakest of the four fundamental forces of nature. It's 19 or 20 orders of magnitude weaker than the electromagnetic force, which in turn is much weaker than the two nuclear forces. It has no natural explanation in physics theory why gravity is a weak force without bringing in grand unified theories or theories of everything. And one of those theories of everything is the kind of theory that involves extra dimensions of space, and it's called brane theory in some parlances. And in brane theory, you can create a mechanism whereby gravity is naturally weak because it bleeds in from these superior dimensions where intrinsically it may be much stronger. So it's an explanation posited in as yet unproven and even really untested advanced theories of physics that unify the four forces of nature. So I think that's where we'd have to leave it. It is pure speculation. I don't think it's necessarily an explanation until these theories have independent affirmation. So the weakness of gravity itself is not evidence in favor of these theories. They need other kinds of evidence to bolster them and to make people believe in them.
Excellent, thank you. The next question is from Kensington 100. Excuse me. Spontaneous particle creation in a vacuum, is it dependent upon the constant expansion of space-time?
No, it appears to be a property of the vacuum of space that can happen, of course, in the lab. Spontaneous particle creation, particle-antiparticle pair creation and annihilation has been observed in the lab going back 50 or 60 years. So it's a phenomenon that doesn't need any cosmic context to explain it, as in expanding space-time. It posits that the vacuum is a place of potential. It's not nothing. And the fact that we can see these processes playing out says that that is the case. And in fact, in some experiments, like the Casimir experiment, you can see that the vacuum is able to exert pressure, which associated with the creation of particles from the pure vacuum.
The next question is from Rama Ranganathan. There are reports recently of two supermassive black holes merging 9 billion light years away from Earth, sending gravitational ripples, which we are witnessing. What are the implications of this on Earth? And did they affect any stellar objects en route, like disturbing their orbits?
So gravitational waves from black hole mergers have now been seen for 4 years since LIGO, the Laser Interferometer Gravitational Observatory, made its first detection. And of course that incredible result led to the award of a Nobel Prize a few years later. These recent detections are from very large distances. 9 billion light years is well towards the beginning of the universe. It's 2/3 of the look-back time towards the Big Bang. And when these gravitational ripples or space-time ripples propagate through space at light speed, they disturb everything they pass through, but by a very tiny amount. So at the moment, the disturbance of these gravitational waves passing through the universe and through galaxies and through stars does not produce a detectable effect on those intervening objects. However, there are experiments that involve using gravitational waves affecting pulsars. So very highly spinning, accurate clock stars are the exception to this statement, where it is possible for gravitational waves to perturb the timing signal of a fastly spinning pulsar in a way that we could detect it. And so people are planning to use pulsar networks as essentially gravitational wave detectors.
Excellent. Thank you very much. The next question from one of our participants who's live, H. Bin Biham, asks, what is it about the physics of red dwarfs that leads to so much activity and flaring that life on planets in the habitable zone might be impeded?
That's a good question. So all stars have magnetic fields because the material that they form from, the diffuse gas clouds that they collapse from, contain low-level entrained magnetic fields. They're mostly turbulent, but they have some systematic properties, and the fields, of course, get amplified when the star contracts and forms. So red dwarfs, in the nature of the way they form, they're quite dense objects, and so their entrained magnetic fields are quite significant. So even though they're low mass and low energy stars, they do have strong magnetic fields for their size. And that means they have strong chromospheric and coronal activity. So that's the real reason. It's the strength of the magnetic field of red dwarfs that leads to their activity in their atmospheres, particle acceleration, and a radiation environment that indeed might make it hard for life to exist on a planet around a red dwarf.
Excellent. Thank you very much. The next question is from Relegate 222. Can you discuss space-time in terms of how we think of time on a macro level?
Well, on the macro level of space-time in the universe, as it's explained in general relativity as a mechanism for how the universe behaves and how space-time expands in the cosmological model that we have. In the normal parts of space-time where there are no large or massive objects, weak gravity situations, the impact on time is minimal. And so clocks just function normally, and they don't have any alteration in their behavior. Clocks are only altered in locations where there's substantial mass density, and that's also true of space in terms of its warping and curvature. So we really only need to apply adjustments to time, the uniformly flowing time that we expect to occur throughout the universe in those very small localized situations of strong gravity, and there indeed clocks are altered in their behavior.
The next question is from an email, and this participant would like to know, are all the photons ever created still in existence, or do photons exist an infinite time?
That's an interesting question. So obviously there's been a lot of photons in the universe over cosmic time. There are all the photons released by all the stars that have ever lived and all the galaxies that exist throughout the cosmos. And those photons are essentially eternal because most of those photons travel through space. Remember, space is mostly empty. So the reason why photons might not be eternal or live forever is that essentially they get absorbed. And then, of course, they raise the temperature very slightly of the object they get absorbed by. So some fraction of the photons produced by all the stars in the universe do get absorbed, but the vast majority do not. And so those photons have been traveling through space. And of course, generally, the photons from large distances in space have been redshifted by the expanding universe. So those photons are eternal, essentially, most of them, but their properties are changing. Now, the bulk of the photons in the universe are not all the photons from all the stars and all the galaxies, but the photons left over from the Big Bang, the microwave background radiation. And that radiation is also essentially eternal because it's at such low level and such a low energy and at such a long wavelength of microwaves that there are very few mechanisms for absorbing it. It can be scattered sometimes, but it's not usually absorbed. And so those photons will persist essentially forever, their wavelength continuing to get longer as the universe expands.
Excellent. Thank you very much. The next question is from one of our live participants. Johnny Mojo asks, When the JWST telescope becomes fully operational later in the year, what do you hope for it in terms of new discoveries?
Well, the James Webb science program is pretty much determined. So it has an early science program which is designed to observe, major categories and important objects just in case in some terrible scenario it doesn't last very long. The telescope lasts 6 months or a year, that you get some important science out, that you don't leave it to chance. And then also in the first year, there's a set of science programs that were in the first wave of science programs approved. It's very hard to predict what discoveries a new telescope will make operating in a new regime. One project that I know about, because one of the PIs of it was a former student of mine here at the University of Arizona as an undergrad, Caitlin Casey. She's now at the University of Texas, and this project got the largest allocation of time to someone who wasn't associated with one of the instruments in the first round. And they're doing a survey of a patch of sky called the Cosmos region, super deep, and as large area as possible to look for new types of early galaxies in the universe. And that's the kind of survey not focused at a particular target where you do have the possibility for significant discoveries, new types of objects, particularly massive early galaxies or galaxies very early with massive black holes that are surprising. It's hard to tell. It's hard to make predictions, of course, for a new facility.
Excellent, thank you. The next question is from Supreme Scientist, who sent an email. Wouldn't it be more accurate to describe the astronomy done by early civilizations, as in Babylonians or Egyptians, as pre-scientific, since they attributed a supernatural cause to explain their observations? If NASA or an astronomy department of a university in modern times were to incorporate magic, superstition, and religion into its paradigm, we would quickly dismiss them as pseudoscientific. So why are early societies given more latitude?
Well, it's a good question, but I don't think they're given more latitude necessarily. I think the people who do historical astronomy, that's not just professional astronomers dabbling, but the people who are historians of astronomy, they're quite careful and actually scrupulous about how they categorize what early civilizations do or did. And I think the way they would describe it is that those civilizations and societies were indeed pre-scientific. They were not operating according to the rules of science or according to formal logic or according to the evidence-based reasoning that we consider a hallmark of science today. And so in that sense, they are not in the same landscape as modern science. However, they were making systematic observations. They were trying to explain things. They weren't only appealing to supernatural entities because they wanted to run their societies, they wanted to have calendars, and so they needed to observe patterns in nature and regulate nature and measure things reliably enough that they could make predictions. And those are the hallmarks of science. So they definitely had elements of what they did that were scientific, but not the whole package. They were not fully thinking in that way. And yes, they did appeal to supernatural entities because they could not explain the universe they lived in fundamentally.
The next question is from Star Stuff 2, who is on with us live. I've been reading about Colmena, the first Mexican lunar project involving mini robots, a plan to derive oxygen from the moon's crust, and a NASA's Peregrine Mission 1 to send science experiments to the moon. Have these kinds of projects been going on for quite a while, or is this a sudden renewed interest in the moon?
This is renewed interest in the moon. The moon is having a renaissance, if you like. So around 50 years after the Apollo series of landings and the astronauts bringing back, I think, 370 kilos of moon rocks, most of which are still stashed at Johnson Space Center in Houston, there is renewed interest in the moon. And that's for several reasons. First of all, there's a lot more players in space now than there used to be. That's the private industry sector, of course, but also governments that had not traditionally done space travel. Emerging economies like India and Brazil and other countries are now doing space. And also with miniaturization, the technology for sending robotic missions, miniature robotic missions, is much better than it was 10, 20, 30 years ago. So the moon is an attractive target because it's obviously, far closer than Mars, so it's much more manageable as an extraterrestrial target. It's obviously much more challenging than doing something in Earth orbit, which is only a couple of 100 miles away from the surface. as opposed to 250,000 miles away. So that's the draw and the attraction. It's feasible, but it's challenging. It's a place to test your ideas and your technology. And yes, these missions, the three you described, represent new players and new ideas on how to approach the moon. And of course, behind all this is the possibility that there may be a moon base, a sustained human presence on the moon, not just astronauts visiting for a couple of hours or a couple of days, but an eternal or permanent moon presence. And that requires the demonstration of some new technologies, such as those that would extract oxygen and water from the lunar soil, and others that would turn the lunar soil into building materials. And I think various entities are trying to demonstrate those technologies in the next decade.
Excellent. Thank you very much. The next question is from one of our live participants, Venpack1. Is there any particular direction for universe expansion? Let's take a case of the Milky Way galaxy and which direction it can move.
No, there's no sense of the cosmic expansion in the sense that if we measure the redshift of galaxies in any different direction using telescopes and how that relates to distance, which is the Hubble relation, that was the evidence for the expanding universe almost a century ago, we see the same pattern. We see the same pattern of redshifts, the same trend of redshift with distance, which is the Hubble parameter. And so there's no sense that there's a different expansion in one direction versus another. And the Milky Way has no special place in this expansion either. The Milky Way does, however, have motion because the Milky Way is on a collision course with Andromeda, which indicates the gravitational connection between those two galaxies. And the local group, the entire local group, including those two big galaxies and the Magellanic Clouds and a few dozen dwarf galaxies, is falling into the Virgo cluster. And the Virgo cluster itself is part of the Coma supercluster, and it has a motion with respect to that. So on various different, much larger scales, there's net motion of galaxies with respect to the what you call the inertial frame, or the frame of reference of the entire universe, which is defined by the microwave background radiation.
Excellent. The next question is from Isla137, who is on with us live. The ending of the question is a little garbled, but the basic premise, I think, is very interesting. So Isla, if you have any corrections, please let me know. Hello, Professor. Why is element burning sequential in stars, and why does it get faster in stars as it goes on? I mean, is the basic.
Right. So the nature of fusion, what we call burning, is a colloquial term, and scientists try to be scrupulous because burning is really associated with combustion as a chemical reaction, and what's happening in stars is not combustion. So scientists use burning. Sometimes they're sloppy or colloquial and use the phrase burning, but really we should just call it fusion because that's what it is, nuclear fusion. So it does have these two attributes generally, which it appears to be sequential in that the heavy elements are formed after the lighter elements, and it does appear to be in a crescendo where the creation of the heavier elements takes less time than the lighter elements. To the first of those, it is not actually purely in parallel. What happens in a very massive star, which is able to create heavier elements, is the heavy element creation occurs in shells within the star. So in the center of the star, even though most of the hydrogen has been consumed and turned into helium, there may still be some residual helium fusion. And even though the star may have moved on, for example, to creation of silicon, a much heavier element, there may still be some fusion of helium into carbon. So actually all the different levels of fusion do actually occur in parallel. And the heavier elements are just added in as the star reconfigures and gets hot enough to start those heavy element reactions. And so that's what the star does. These things are actually happening in parallel, where the hottest regions are near the center, and that's where the heaviest elements are being created. The crescendo aspect is a natural consequence just of the relatively small amount of fuel. The bulk of the star, of course, was hydrogen and helium when it started its life. And after that first phase, it's turned most of the hydrogen into helium. There is much less time for the other reactions because they're occurring at an enormously higher temperature. And so it's temperature-driven rate of reaction that causes the crescendo. For example, the heaviest elements in the core of a star, when the iron is created, are occurring at a temperature that's 40 or 60 or maybe even 80 times hotter than the temperature that creates helium from hydrogen. So that the limited availability of fuel that hasn't been fused and the incredible temperature and rate of reactions is why it happens like a crescendo.
Excellent. Thank you very much. The next question is from Azure Vision. Thank you very much for the excellent astrobiology course. What would be your recommendation for further education in astronomy and astrobiology after finishing the Coursera courses? For example, how much more would you need to learn before you could be of any use whatsoever doing basic astronomy research work at the University of Arizona?
So the distinction between the MOOCs that many of you have taken, massive open online courses, and formal coursework in astronomy is significant. It's not a huge difference, but it's significant. These massive open online courses, the ones that I teach and others like me, are sort of equivalent to our introductory astronomy for non-science majors classes at a university, at any major university. If you were going to study the subject or do research in it, you'd have to take the kind of classes that astronomy majors take. And they will, of course, in the first couple of years of these programs, they will cover the entire subject from planets to cosmology, but they'll do so in a way that involves much more physics and much more mathematics. So you'll be getting the formalism of astrophysics and mathematics behind it, and not just a descriptive version of the course. That's a big distinction. And that means the commitment required and the background required of math even before you start is significant. Students who have astronomy, who are majors, have to have calculus. They do pre-calculus. They take 2 calculus courses before they really even start their formal science training. So I think that's the biggest difference.
All right, the next question is from Hernan, who is on with us live. Triton seems to be the poor forgotten moon that no one mentions. As far as I know, it has never been explored in depth. Can you talk a little bit about what information we have on Triton regarding possible, re-evolution of life 2.0, and if there are plans for exploring it in the future?
Yeah, Triton is indeed maybe forgotten. It's one of the icy moons of the outer solar system. It's of substantial size, not as big as it's not as big, for example, as the Galilean moons, of course, or of Titan around Saturn, but it's maybe half or a third of the size of those other large moons. So it's substantial size. It's extremely cold, of course, right at the outer solar system, but it has some activity, and it's in one of the objects where the body's properties, as well as we can measure them very indirectly, because we've only ever had a couple of probes that went out there in the 1970s, essentially, is almost certain to have liquid water under its surface, kept liquid by radioactive heating from the core and by pressure from the icy layer on top. It's just a substantial enough moon that it's likely to be mildly geologically active and to have liquid water. And so it does have biological potential. And our level of ignorance of it, of course, is very high. So it really will take a new outer solar system mission. Outer solar system missions are really difficult. NASA only really gets to plan one at a time. The timeline for them, of course, is roughly 10 years to plan and build and 10 years to go out there and get the data. So they're 20-year commitments. At the moment, Europa is getting the attention with the Europa Clipper. Europeans and NASA are both doing Europa missions. And there's also a Titan mission on plan to send the helicopter or quadcopter around those methane lakes. I would say Triton is perhaps in the next tier of missions that people might consider, and I've seen white papers that talk about missions to go that far out, even quite recent white papers. But there's no sign of a funding line, and there's no commitment by NASA of funds to such a mission yet, which is a shame, but it all takes time.
The next question is from Christy Reed, who asks, should the space treaty be renewed as soon as possible?
Yes. Hi, Christy. Christy is a great, of course, supporter. Many of you may have encountered her behind the scenes as a mentor, helping so many of our students over the years. So the space treaties are very important to renew and revisit and revitalize and extend, because they all pre-exist the enormous boom in space activity that's happened in the last decade, and especially just in the last few years. So really all we have is the Outer Space Treaty of 1965 and the Moon Treaty of 1979. And the Moon Treaty has very few signatories. The Outer Space Treaty, which bans nuclear weapons and offensive weapons in space, was signed by almost every country. So there has been push in the space-interested parts of the United Nations organization to getting a new treaty on the books. Essentially, I would say supplanting the Moon Treaty of 1979, because the Moon Treaty of 1979 said that governments and countries couldn't own real estate in space, but it didn't say anything about corporations or individuals, which is really the important thing right now because of the private space sector. So yes, there are commissions in the UN that are actively looking at developing a new treaty, or maybe even a set of treaties or agreements that will govern space into the future, and they will deal with issues that were never resolved in the 60s and 70s, and they will also re-up or reinvigorate the prohibition on weapons in space, which is one issue that gets many people concerned.
The next question is from an email from David McKenzie. David asks, how do we communicate with the rovers on Mars when Mars is directly opposite the sun from Earth? Also, will this present a problem when we send humans to Mars?
Well, we communicate with the rovers, and it just takes longer. I mean, so depending on where Mars is in its orbit relative to the Earth, it can take, I think, anywhere from 8 to 25 or so minutes to communicate with the Mars rovers. And that's the delay time, that's the lag time. And so the Mars rovers are built in an interesting way. At one extreme, you could just be completely hands-off. You could just give the Mars rover over to AI, to internal AI that they had on board that would let them make all the decisions of where to go and what samples to pick up, and just buffer that information and send it back to NASA. So NASA would have to create that capability, then be hands-off and just deal with the information and trust that the AI was going to protect the rover and get the best scientific return. AI is not mature enough that NASA's ever decided to do that, and it may not even decide to do it soon, because AI is still not mature enough to risk your very expensive hardware. So at the moment we sort of have a hybrid. The hybrid is that it does sometimes require real-time maneuvering, which is when the rovers are in precarious position and they're not just traveling over flat terrain. There are often pauses put in their programming where we actually do wait for the signal to come back and the images to come back from the rovers before people in live situations in a mission control center make the decision of what should happen next. So that does happen, and that involves waiting that awkward amount of time, which can be long or short depending on where Mars is. But also the rovers are built with pre-programmed sets of commands. So the rovers have sort of batches of commands, a day's worth, say, or a fraction of a day. Remember, the rovers rarely travel more than a few tens of meters in a day. I think if they travel 50 or 60 meters, that's a good day. So they don't really go that far, and you already have maps of the terrain they're covering. So in those terms, you can bunch up a set of commands of the rovers in an automated way, traverse a certain terrain or approach a certain rock and try to drill and maybe get a sample or a chemical measurement. So that's sort of how the rovers have been operating, and I think that's how they will for some period in the future.
And does that also answer how we're able to communicate with humans? So how would we communicate with humans when they're sort of opposite us, behind, quote, behind the sun?
So to ask the question and make it a separate question on how will we or do we communicate with humans when they're on Mars, because we think that'll happen in the future. I think when people are on Mars, the time delay of the communication, which is really awkward, it does not give you the time, does not let you have a real-time conversation, is such that they will operate essentially autonomously for all practical purposes. If they have to make decisions, they're not going to wait 20 minutes on a small decision or even a medium-sized decision. to get affirmation from the Earth. So the people who go to Mars will essentially be operating on their own steam, if you like, and so they'll make their decisions in their real time. But they will, of course, be advised and at some level controlled by what happens on the Earth. So there will be sort of major mileposts or major times when they are tethered to, the signals from the Earth and the ability to communicate with the Earth and get approval of those kind of decisions. But you can't if you did it all the time and routinely, it would be impossible. So it only happen occasionally and for big scale decisions.
So that's really interesting. So it's mostly a time delay issue, not an interference issue. Is the sun being in the way? Like, can we do the radio signals go around the sun? Like, how do
So in the direct sense of yes, there obviously is a particular orientation or alignment. I mean, if Mars was really occulted by the sun, then that would be a problem. You'd be blocked essentially, any radiation, including radio waves. But except for that, and that situation, due to the speed of the orbits, that would not persist for more than a couple of days. So indeed, you may have blackout zones due to the orbit. It is possible. Remember that Mars and the Earth have slightly different inclinations on their orbits. So Mars, Earth, Sun eclipses don't essentially happen very often at all. They're extremely rare. So that type of direct blocking is very unusual. But in the near term, when the angles are close and the path is close to the sun's chromosphere or high radiation environment, yes, it can interfere with those radio signals. So I would say there are probably zones of a few days to maybe a week at a time, occasionally, when these communications would be very difficult, if not impossible.
Excellent. Thank you very much. Ron CC asks, hello, Professor. Can you tell us more about infrared imagery and how we make images from IR signals, knowing that the visible spectrum is a smaller range than the IR spectrum?
Right. So infrared imaging is a simple extension of optical imaging. So optical imaging essentially uses CCDs, charged coupled devices, and they've been around since the 70s, and of course every phone has one in it. So there are literally billions of CCDs in the world now. There used to be very few back in the 70s. They were research-grade imaging devices, and astronomers essentially use, very fine, large, and pristine versions of the CCDs that you would have in a cell phone. For infrared imaging, it's a related technology, but you're obviously responding to longer waves. It's essentially heat. So depending on the wavelength, infrared imaging can actually be heat sensing. So if the wavelength of the radiation is longer than about 2 or 3 microns, then you actually have to shift to a sort of heat sensing technology, where essentially you're using a semiconductor substrate to measure heat. You're measuring that thermal effect of the infrared photons arriving and being detected. And those, they're not formally like CCDs, which are silicon detectors of optical waves. They're heat detectors, and you can put enough pixels together to make a very simple imaging device, but it doesn't have anything like the megapixel capability of our optical phones. So that's long wavelength beyond a few microns. In the regime between about 0.9 microns, which is the far red end of the visible spectrum, and 2 or 3 microns, which is the near infrared, then you have devices that work analogously to CCDs. They just have different electronic substrates. They use for example, indium and antimonide, or mercad telluride, which is a triple hybrid of elements. So you're using different types of semiconductor materials which respond to those longer waves. And you have the same thing. You have pixels, you have readouts with wires on them, so that you can get the signals from each different picture element of this silicon, of this semiconductor substrate. They don't tend to be quite as big as optical CCDs. Again, the technology is not quite as advanced, but they work in a similar way.
Excellent. The next question is from HBinBHM, or HBinBHam. I'm not sure if I'm saying that correctly. I apologize. I heard that Jocelyn Bell Burnell recently said she thinks time domain astronomy is one of the most interesting in astronomy today. What does this entail, and what questions does it ask and answer?
Yes, Jocelyn Bell Burnell is, of course, made her name in time domain astronomy because she is the discoverer of pulsars back in 1967. She was a graduate student at the University of Cambridge, and working with her advisor Tony Hewish, she found periodic signals from what we now know to be pulsars. And so I know Jocelyn, she's a colleague from the UK. And she's right that time domain astronomy, which is how she got her reputation and how she made her discovery, is enjoying a resurgence where very big projects are now using time domain. The idea is that we don't really know all the phenomena in the universe that involve changing objects or objects that change. So if you stare at things in a sort of unconstrained way, even things you don't think might change or where anything's interesting is happening, you will discover things. And so the discovery potential of time domain astronomy is large if you can do surveys. And the ultimate expression of this opportunity and possibility is what's called the LSST, the Large Synoptic Survey Telescope. In Chile, it will survey using one of our primary mirrors built at the Mirror Lab in Tucson, Arizona. It will survey the entire southern sky to about the depth of the Hubble Space Telescope's capability every 3 days, and it will do so in multiple wave bands. And it'll just do that over and over. And it's the shorthand or the catchy title for this type of science is called celestial cinematography, and is undoubtedly going to lead to some interesting discoveries within 3 to 5 years when that telescope gets going.
Cool Pool Party, who's on with us live, asks, with all the medical challenges involved with a human mission to Mars, is it near-term feasible?
Yes, it is, because people will just accept the risk and the challenges. That's the history of the space program. The first people, who went into orbit back in the 60s, knew they were sitting on top of, essentially chemical bombs that could go off and kill them, and they did it anyway. So the risks in space travel have always been substantial. The astronauts who went to the moon didn't know if they could get back, and nearly with Apollo 13, 3 didn't. But they luckily all did, and so people have survived this. The moon or Mars will present another set of risks. The medical risks are significant, but they're probably not as big as the risks of a catastrophic failure of a launch vehicle or a landing vehicle or the environment which they built to live in, their sort of habitat, if you like. So these are substantial and at the moment not fully quantified risks. And people are trying to design what living or working on Mars and the moon will look like to be able to define those risks better. But the people who go, those first people, they will sign waivers, of course, but almost the waivers are irrelevant because these are people who fully understand the risks and think that because they're doing something so extraordinary, it is worth the risk.
All right, the next question is from Robert Uram, who sent an email. What would the sky look like if I looked at it using infrared goggles?
Well, if you were watching the sky with infrared goggles, and of course we've done this now because we've had infrared telescopes. So the Spitzer Space Telescope was the first purpose-built space observatory with great sensitivity in the infrared region. So if you were looking at the universe or through the sky or any part of space with infrared eyes or infrared goggles or infrared telescope, you will see essentially cool objects because you're essentially looking at heat radiation. So things like the sun and all the stars will be less prominent. The things that will be more prominent are cooler objects. So perhaps the coolest forms of stars like red dwarfs or brown dwarfs will be more prominent relative to optical observing. Planets will also be more prominent because the temperature of planets is hundreds of degrees Kelvin as opposed to thousands or tens of thousands of degrees, and so they emit most of their radiation in the infrared. So you'll see warm things and medium hot things. You'll see planets more easily than you could in the optical. That's quite a large factor, maybe a factor of 10, and that's a big difference of what you see with infrared eyes.
The next question is from Star Stuff 2, who's on with us live. In the light of Russia's invasion of Ukraine and increased Russia-U.S. tensions, what are the fears on how this might affect the International Space Station, but also other astronomy projects?
Well, there's been an enormous effect already. It's only 2 weeks as we speak into this invasion, and the consequences for Russia, are, of course, are severe. The scientific consequences are playing out every day. They don't make as many headlines, so you won't see it in the newspapers. But in the science journals, you can see it every day, and they're substantial. NASA is withdrawing pretty fully from partnership with Russia, and that affects the space station, the future of the space station. It affects launch vehicles and rockets and various collaborations on scientific missions that we were doing with the Russians. So people tend to forget that through the ups and downs of the Cold War and détente and then the current tensions or the recent tensions, the scientific communities of the United States and Russia have been fairly well aligned and fairly collaborative. And that's, of course, falling apart very rapidly. So pretty much day by day, I see new headlines of projects that are being put on hold, collaborations that are put on hold, investments that are put on hold, withdrawing from major projects is already happening in scientific arena and physics especially. And I think the worst consequence, which is not clear how it's going to play out, is on international students. It's a very recent story, but Eric Swalwell, who's in the Congress representing California, had essentially argued that we should send all the foreign students from Russia home. And that's a pretty severe consequence for students who came here to study science and may have no political opinion at all, and certainly may not implicitly or explicitly support the current regime in Russia. So some of these consequences for people, for Russians, who are really not responsible for what's happening from their government and haven't maybe even lived there for a while, are pretty severe. So these are difficult conversations that we're having in science right now.
Thank you very much for addressing that, Chris. Tegan PS asks, thank you for providing these amazing courses. What got me interested in astronomy and astrophysics was actually the film Interstellar. Can you talk about how scientifically accurate the film was?
Yes, Interstellar was really an excellent film. I mean, I like to enjoy films that include science. If the science is moderately well done and they don't bend the rules too much, then I can withhold my judgment or suspend my judgment if they bend the rules a little. Interstellar, in that spectrum, was a movie that took the science pretty seriously and did a good job. And probably the best sign of that was that the major scientific consultant on that film was Kip Thorne. Kip Thorne is a esteemed professor of physics at Caltech, winner of Nobel Prize for the LIGO work, theoretical LIGO work, and he was the consultant, and he was the one who essentially was feeding from his research group simulations, black hole simulations on supercomputers to the directors and the producers and visual designers to try and make sure they got that right visually. So it was really very unusually accurate for a film and an unusually interesting subject matter as well. So that's an unusual category. Most films that involve science don't quite get it right as much as Interstellar did.
The next question is from Venpak1, who is from India. They would like to join a space program, but India does not have a manned space program. Is it possible to join a space program? And maybe they mean manned or unmanned, but is it possible to join a space program in foreign countries? And how does somebody go about doing that?
Well, sure. I mean, it's very international, the space arena. Now, India does have a space program. It's a very active space program. It's been growing, and India's been to the moon just in the last year or so. And India does have a plan of, not near term, but a mid-term plan to actually go to the moon with people. They don't have that capacity right now. But so India's very ambitious in their goals for their space program, and they've achieved some landmarks in the last few years. But the astronaut program, or going into space, has been international for a long time. So Indians have been to the International Space Station. There have been Indian astronauts, without the Indian government sending them up. It's happened because they've been trained and they've been selected from international pools of people. And so I don't know the actual number. I think it may be 25 or 27 countries have been represented by the people who've been on the International Space Station.
Excellent. Thank you very much. Ambrogi 7, are you or your group in Arizona directly involved in any of the research with the Webb telescope, the James Webb Space Telescope? And can you talk a little bit about that involvement?
So I'm not directly involved in any proposals right now, and our group with Matthew and our students is mostly doing education research. So we're not doing astronomy research that would use the James Webb. I still do some astronomy research, and so I do have colleagues in the department where I'm, certainly toying with the idea of putting a proposal in. The first round of proposals has already been selected for the first year of observation, so this would have to be downstream of that. And obviously we have a lot of James Webb involvement in Arizona because we have, in Marcia and George Reiki, we have two of the PIs or principal investigators of two of the James Webb's four instruments, and they have a lot of time associated with being leads of those instruments. So there's a lot of activity here. There's a lot of collaboration here, and there are a lot of opportunities. So I would not rule out that I might get play my hand into that in the next year or two.
Excellent. Kind of a more fundamental question from Faisal, who sent an email. Why does the light from distant stars shift to red?
Well, from distant objects, the shift to red, or the redshift, is essentially driven by the expanding universe. So as the universe evolves, space-time is expanding. That's the fundamental premise of the cosmology that we believe is correct, and it's based on an explanation in the general theory of relativity for how that happens. So expanding space-time essentially means that the matrix, the underlying matrix of space itself is expanding. So if you could imagine an invisible grid that in X, Y, and Z dimensions marks out space, that grid would be expanding. Those markers would just be getting further and further apart. It also means that any wave that travels through that space is subject to the same expansion because its wavelength is obviously referenced to the fundamental markers of space. And so the wave is getting longer, and that means redshift. So that's how the redshift happens.
Excellent. So we have a really interesting question that I don't think we've ever addressed before, so I'm excited to hear your take on this. SO Moon, who is Muskan from India, would like to know if there is a link between the fashion industry and space industry. They're currently majoring in fashion, but highly interested in space and astronomy. I always include my knowledge in my collection for colleagues, but do you think there are going to be fashion designers in the space industry in the future?
Yeah, I mean, it's an interesting question. It's a niche, but I would say it's a niche that actually already exists. I would say the fashion designers are probably not going to be employed by NASA or any of the international space agencies. Those agencies traditionally have not shown much interest in design principles. They may design a logo here or there, but they don't really get interested in the fashion aspect of, say, the suits the astronauts wear, for example. That's just not a tradition with them. However, this private space industry is something different entirely, and I already remember, and you can find pictures of this online, that not Blue Origins as much, but definitely Virgin Galactic, when Richard Branson was first proposing sending people in suborbital flights, he made a big deal when he was showing off his first launch vehicle of the snazzy suits they designed, the Virgin Galactic spacesuits, or jumpsuits almost, because they're not pressurized. That's not required in their flight. And so that happened there, and I'm sure he had a high-end designer for that. And Elon Musk, of course, is the other logical person you would expect to take that seriously. And as anticipated, SpaceX has paid a lot of attention to fashion and design and how they do, and their spacesuits and their jumpsuits and so on are also very nice. They're very modern and very obviously well designed. So the private space sector is definitely employing fashion designers. There's no question. Maybe not that many, but they're taking it seriously.
And so the other question that SO Moon has probably doesn't have an absolute answer. They would like to know if having some kind of background in astronomy might help them, but since it's not really a field, It's unclear how to get into it. Do you have any advice?
Yeah, I think space fashion, if you like, is such a small niche that there's no obvious path or no advice you could really give anyone, except that the people, except to look to the private space industry and who's doing who has the most activity, who's doing the most work, and therefore who's the most likely to employ the talents of a fashion designer. And in the end, if this industry grows, then even those three space companies I mentioned, Blue Origin's included, they also have clearly fashion designer inspired space suits and jumpsuits. That's going to grow, but it'll grow modestly. And so, yeah, you'd pretty much have to have an inside connection to get your foot in the door, I think.
Charan Basaretti, who's on with us live, asks, why aren't the space programs more interested in exploring the moon instead of Mars?
Well, I think the space programs are getting interested in the moon, and they've never not been interested, to use the double negative. And that's because, so there are two reasons. The main reason it seems like they're not interested is just Mars is sexier, hotter, more difficult, more challenging, more evocative. There's plenty of reasons why Mars sets a deep hook in the consciousness of the public or even of other scientists and explorers. To go to Mars would be incredible. But NASA and all the space entities know that the moon is far easier than Mars, and that to learn how to live on Mars, you probably need to learn how to live on the moon first. So Mars has the moon as a stepping stone, and it's almost certain that whatever happens on Mars will happen on the moon first. So the moon is not actually being neglected in these plans. And NASA has a set of collaborations called the Artemis Accords, and the Artemis Accords are based on how it will collaborate using partnership with SpaceX amongst other entities to go to the moon and set up a orbiting infrastructure around the moon as well as a base on the moon and then on to Mars.
Excellent. Thank you very much. The next question is from an email that we received from Steve Callender. In a multiverse model of the universe, what we perceive as dark energy be the gravitational effect of an infinite number of universes? What are sort of the implications of such a possibility?
I mean, as you frame it, that is of course a possibility, but the truth is the multiverse model, and I'm not going to elevate it to the name theory because it's not a formal theory. It's just it's a concept, it's an idea, it's a model. Has so little boundaries on what it could mean, on how it will play out, that it's not formally predictive. I think that's the main criticism of many scientists or even some cosmologists about the multiverse idea, that it's not a richly predictive theory and therefore a productive theory. They view it as pure speculation. So I'm afraid that's the unsatisfying answer, that multiverse theory is so speculative that you can spin out all sorts of possibilities, including the relationship of these unseen infinite number of universes on dark energy, but there's no way to test that idea in particular, or even ideas in general about the multiverse yet.
The next question is from Honor Day. Could you explain density wave theory? Do you think it could be a better explanation for spiral arms than stochastic self-propagating star formation?
Right. So the question relates to the idea of what causes galaxies to have spiral arms. So the first thing you can say about spiral arms of galaxies, including our own, the Milky Way, are that, as you might anticipate, the spiral arms trail the direction of the spin. So you could look at the spiral of the Milky Way, and it's as you would intuit. The arms are trailing, going backwards, as in the direction away from the spinning of the galaxy. But after that, it gets more complicated. If you just imagine the spiral was in place and then the galaxy just winds forward in time, then the galaxy would wind up by so many revolutions. The Milky Way has spun over 20 times in its history, that the spiral arms will get impossibly tightly wound, and that we don't see that. And so right away, you know that they can't be fixed features. So the first thing is you rule out that the fact that they're fixed features just evolving with time, because that doesn't work. So you need a different explanation. And the two explanations are stochastic propagating star formation, which essentially means patches of star formation sort of propagate through a galaxy like a contagion. And that, coupled with differential rotation, where the central parts rotate more rapidly than the outer parts, mean that you could end up with something that looks like a spiral pattern. The density wave theory, which actually goes back further, that theory goes back to the 1930s. Stochastic star formation propagation is the 1980s, I think. So the density wave theory goes back a long way, and it essentially says that the spirals that you see, that the stars that are part of the spiral, the prominent stars that form the spiral, are not fixed features. Those stars are moving in and out of the pattern, but the pattern is what we see. And so it's a density enhancement that creates more visible stars, or a larger number of stars in that particular region where the density is higher, but the stars themselves are moving in and out of the pattern, so it's not a fixed set of stars. And at the moment, the jury has always been a little out on which of these two theories better explains the data, and I don't think really that's changed recently.
All right, thank you very much. This is going to be our last question for today. Abhishek Parekh would like to know, what is the average cost of pursuing a master's or PhD in astronomy or cosmology in an American university like ours?
Well, that really depends on the mode of your support. So graduate students at our university, or all the major research universities that have graduate programs in astronomy, graduate students are usually supported. And so when a graduate students get submitted to a program, in ours, for example, the offer of admission contains an explicit, in writing, offer of 5 years support, because that's how long it's presumed to take you to the PhD. And in practice, if you take a 6th year, that support is there too. And the funding mode comes from two main sources. It comes from grants from the faculty members that you would be working with as a research student. So if you're doing, publishable good research, you're probably working with a faculty member who has a grant, and that grant will have money built in to pay you as a research assistant, or RA. If you're in a department that teaches astronomy or teaches large classes, then you also have the possibility of a TA, or teaching assistantship. And so graduate students at our program, and in many others like ours, have their funding year by year from a mixture of RAs and TAs. And most students, have more RAs than TAs because they're essentially doing research. And then some fraction of their funding, or the funding of students in a whole program, comes from fellowships from outside entities like NASA or NSF or foundations. So generally the cost, really the intention in a good program, the cost to the student is nothing. You should not come out of a program like that with student debt. Because if you go to a program that's high enough reputation and quality, it will contain funding mechanisms within the program to support you. Now that's just to cover, of course, your presence in the program and your tuition and so on. You still have to have room and board, and you have to live. But those stipends tend to be enough. Our students get paid enough that in Tucson, at least, where the cost of living is not too high, they do fine. So that's a good question to end with on a different note, and a lot of interesting range today, as always. So thanks to Matthew and Grant for running the session, and we have our next couple, I think, on the books. I won't hazard my memory by telling you when they are, but you'll see the next few sessions coming up. So thanks for your participation, and we'll be with you next time.
Excellent. Thank you very much for joining us today. Our next session will be on YouTube in 2 weeks on Monday the 21st. But in between there, don't forget we have a time change. So even though we'll still stay at 10 because Arizona doesn't do daylight savings, it may be a slightly different time for you depending on whether your area does daylight savings time or not. So take care, everyone. We will see you in 2 weeks, and then 2 weeks after that. Take care.